The floor is yours.
Yes, thanks a lot, Adam, and thank you all for having me and listening to my talk. So this is about joint work with Andy Wiese, and like Adam already said, my affiliation is kind of outdated. I'm going to Maastricht now, and so is Andy's, who is, I think, now in Amsterdam still, but then he is moving in a couple of months to Munich. So really, to keep up with this institute, I would have to update the slides every week. But anyway, so this is work that appeared in this year's doc, and it's about an approximation algorithm for preemptive weighted flow time on a single machine. So let me start by introducing the problem. And please, if there's something unclear, feel free to interrupt me at any time. Adam told me we have plenty of time, so no worries about that. So the problem, as in most scheduling problems, you're given a bunch of jobs that have to be completed, and in this case, the jobs, they have different release times. So there's for each job here illustrated by a box, there's a specific time from when it becomes available to be processed. Also, each job has a processing time, PJ, which denotes the total amount of time you need to process it in order to complete it. We are only dealing with a single machine here, so we need to schedule all these jobs on this single machine, like for example in this schedule. The important facts here is that no job can start processing before it's released, and every job, well, it has to run for time PJ, and the machine can not process more than one job at a time. What is allowed is that you can preempt the job, so that means I can interrupt processing a job and I can resume it later. And in the end, I need to process all the jobs. Once we are given such a schedule, we can define what is known as the flow time of a job, and this is the time from when it's released until it's completed. So in this schedule, for example, the red job has a fairly large flow time because it was interrupted, and then we first run the yellow job and only finished it quite late. But in general, we want to minimize these flow times. So a schedule is good when we have low flow times, which means no job waits for a long time. And since there have to be some trade-offs between the jobs, one very popular way is to formalize the objective as the weighted sum of flow times. So each job has, in addition, a given weight, which describes how important it is. And we just minimize the sum over all jobs and then the weight of the jobs multiplied by the flow time. So this is a very basic problem, but it has a long history. It was studied in various different settings. For example, here online setting comes to mind when jobs are only known once they are released. Or you can also think about settings with multiple machines, or settings where you are allowed to have speed augmentation or other special cases. But even in some sense, in the most basic setting, the offline approximation setting, it wasn't for a long time not really known what's possible in this problem. And this particular case is also named by Schurman and Vögelinger as one of the 10 most important questions in scheduling, and this survey was some 20 years ago. And so this has a long history of not really us not really knowing what the best approximability result for this problem is. And fortunately, a lot has been done recently here. And to start off, these new results, they started with Bansal and Bruce, who showed that you can actually find a log n approximate solution in polynomial time. And the algorithm, it's based on involved LP rounding techniques, which they in fact applied to a much more general problem. And one of the corollaries of this result was that you can get a log n approximation. Then the first constant approximation algorithm was by Batra, Garg, and Kumar 3 years ago. They combined LP rounding techniques, this time with a novel dynamic programming approach. And they got this constant, which was a big breakthrough, but the constant was huge, so they didn't optimize it. It's something above 10,000, maybe even much worse. You can think a little bit of it as being caused by this LP rounding. So in the LP rounding of the algorithm, this was basically the critical part where they introduced this large constant. And now Andy and I were able to drastically improve this ratio to 2+ϵ for any fixed epsilon greater 0. And the main technique here is just dynamic programming. So we built upon the framework by Batra, Garg, and Kumar, and we simplify the approach to completely get rid of the LP rounding, and this ultimately leads to a drastic improvement of the approximation ratio. Finally, there are two more important works that I want to mention. So there's a 20-year-old quasi-polynomial time approximation scheme by Chikuri and Khanna. So they managed to approximate the problem arbitrarily well, but the running time is quasi-polynomial. This kind of gives the idea that this problem shouldn't be too hard. So if there's a Q pitas, you would think there should also be a pitas. But in this problem, there's a big gap between quasi-polynomial time and polynomial time. And finally, one important technical result was by Feige, Kulkarni, and Lee. They gave a reduction which basically shows that it suffices to give pseudo-polynomial algorithms for this problem. So in general, in this problem, the input numbers, the release times, the weights, the processing times, they could all be exponential. But with this non-trivial result, they were able to show that if you can solve the problem assuming all values are bounded polynomially, then you can also derive a solution for exponentially large numbers. And the result is essentially used in, or it is required in all of the mentioned results here, because for example, Batra, Garg, and Kumar, it was initially a pseudo-polynomial time algorithm, and only in combination with this lemma, it's a polynomial time algorithm. And also our algorithm is based on this and relies on it heavily. So in the rest of the talk, I will just assume that all numbers in the input are somewhat small, so it's bounded by some polynomial in the number of jobs. So I will start off with an integer program, and don't worry, this is a lot of math on one slide, but I will actually explain it very very simple in some geometric way. So we don't have to read it now. let me just say there is an integer program which models precisely this problem, and essentially what we need to do is only solve this integer program, and in order to do so we will use very much the very nice structure of this integer program. And to explain what it means, let me introduce the following picture. So in this picture, the x-axis is the time, and we assume that we are in discrete time, so there are like units of times. Because everything is small in the input, we can assume that we have this discrete time, and on the y-axis, we have sorted the jobs by the release time. So the uppermost row, it corresponds to the job with the earliest release time, and the lowest row, it corresponds to the job with the highest release time. And every square in this picture, it corresponds to a pair, a job, and some time later than its release time. So this is also why the first row, it starts at the leftmost point, and the last row starts at the rightmost point, because the jobs are ordered in this according to the release time. The intuition behind this integer program is that in this problem, it's all about determining when a job is completed. Because if somehow we would know in the optimal solution what the completion times of each job are, then we could solve the remaining problem in polynomial time. So in some sense, we want to find these prefixes here in blue of each row, which correspond to how long the job is alive. So for example, the job J1 in this picture is alive as long as this blue bar goes on. And this intuition is also found in the integer program, because in the integer program we have one binary variable for each of these squares, which tells you whether a particular job is still alive at this particular time. And then the blue constraint also comes naturally, because it just says once a job is completed, it's completed, and it will not be alive anymore. So these variables have to be monotone from left to right. Also, given these variables, it's very easy to write the objective function of minimizing the weighted flow time, because for every unit of time that the job is still alive, we pay a value of its weight. So then the objective is just to minimize the sum of all jobs, the sum of all times, and the weights times the variables which say if a job is still alive at a particular time. But if we had just this, then the problem, the integer program would not model the problem, because we could just finish all jobs immediately. So we need some kind of constraint that tells us, that restricts how fast we complete the jobs. Basically, by incorporating the power of the one machine that we have, by modeling how much the one machine can process. And the constraints that we need for that turn out to be the last kind of constraints in this integer program. And I will not explain that this is equivalent, but instead I will focus on the structure of these covering constraints. It turns out that you can visualize these covering constraints very nicely in this picture by vertical rays. So each of these constraints, and we have one for every interval of time, corresponds to a vertical ray which starts at some point and then goes to -infinity. And if we look at one particular of these constraints, then this lower bounds it gives us some requirement of how many jobs need to intersect with this vertical ray. So recall that we want to decide how long these blue bars go on, and each of these vertical constraints, they say, okay, the jobs of which the blue bars intersect with this vertical ray, they need to have at least some certain processing time. So if you look at the left-hand side of the constraint, then it's a sum over the pj values times the xjt values of the jobs, and the support of this constraint, it exactly corresponds to the jobs or the variables that the boxes that are hit by this vertical ray. So we don't need to verify this. This is an easy task to verify that they all look like this. But let me just repeat. We want to decide how long each of the blue bars go on from left to right, and we pay a certain cost for making the blue bars longer, and we need to have them long enough so that the demands of each of these vertical rays are satisfied. So each of the vertical rays has a certain right-hand side, and it needs to be covered by having enough of the blue bars intersect with it. Okay, I will repeat the problem in a few minutes. So what we are going to do is basically we are reducing the scheduling problem to this geometric problem, and in addition to what I said here, we are also doing some simplification steps to this problem, and once I arrived at the final problem that we need to solve, I will again repeat the definition of what we actually want to solve, and then I will explain how we actually do it.
Can I have a question?
Yes.
So in this ILP, you have constraint for each pair of time slots.
Yes.
And these rays, it seems there are less of them than the time horizon squared, right?
Yes, that's not a, then it's not a correct picture. So I just drew a few vertical lines, but actually, yes, you would have one for each interval of time, so you would have a bunch more.
Okay, but here you define an array as like a time and a job, right? It's two-dimensional.
Yes, essentially, you've defined it by. Can you see my mouse pointer?
Yes.
Yes, you defined it by a time and a job, so one of these squares, and then it will go all the way to the bottom.
Okay, so there are more constraints than rays.
Yes, so it could be that multiple arrays have that there are basically multiple rays on the same squares. In that case, one of the rays would dominate the others, because it would still have the same left-hand side, but the right-hand side, well, then only it matters what the largest right-hand side is.
Okay, perfect. Thank you.
Good. So, as I said, we are going to simplify this problem further first, because one of the issues with this is that these prefix constraints are very hard to deal with. So deciding, well, requiring that we select a consecutive prefix of every row. And instead, we will trade this this blue constraint for some kind of lesser evil. So I will explain now what I mean. Let's take again the same picture, and let's do a geometric grouping of the squares in each row. So I will group the squares together in some exponentially growing way. So I'll take the first square, then I will take the next 2 squares, then the next 4 squares, and so on. So this gives me groups of constraints, and now I will, instead of requiring that I select a prefix of squares, I will require that for each row I will select a subset of these groups. So essentially, of each group, I either select all squares or none of them. So for example, this is a prefix. I'm not allowed to do that. I could, but once I extend the prefix until the end of the next group, this would again lead to a feasible solution. On the other hand, my solution doesn't need to be consecutive, so I could, for example, select the squares in these 2 groups. It's not hard to see that the 2 variants are within constant factors from each other. So for now, I will essentially ignore the factor of 2 that I want to prove and just aim for some relatively small constant. And for this purpose, it's not hard to see that this reduction loses only a constant factor, because if I start with the prefix constraint, I can always, from every feasible solution, construct another solution that also satisfies the group constraint by, like I said, rounding up until the end of the next group. And since I have these covering constraints in my ILP, it never hurts, at least for feasibility, it never hurts to select more squares. So if I add more squares to my solution, I still remain feasible. On the other hand, the objective value might go up, but you can see that because of this exponential growth, I will add at most as many squares as I already have in each row. So this, in the worst case, it doubles the length of every prefix, and this also means it just doubles the objective value. On the other hand, if I have a solution with these group constraints, then I can also transform it to satisfy the prefix constraints by just adding all the squares that I left out. So basically taking the prefix from the beginning until the last square that I selected in the blue solution. And again, this just increases the cost of the solution by a factor of 2, because by this exponential growth, the length of the last group, the last blue group, is already at least half of the length of the whole prefix here. So within constant factors, these 2 variants are equivalent. But so we do this procedure for every row, so we get these group constraints for every row, but now we run into another inconvenience, which is that we have very complicated intersections between the groups of different rows. So if we ignore the y value or the height of the groups, they still could intersect in very non-trivial ways. What we would like to have is that the upper group is a superset of the lower group. And we can actually achieve that by a slightly more involved geometric grouping. You can think of it as, having an exponential growth that's not quite as fast, but it will, in addition, satisfy these simple intersections. So we can define this exponential growth, which also satisfies that each rectangle is basically half of the rectangle to its top. And this exponential grouping was defined already by Batra, Garg, and Kumar. And one of the disadvantages is that it loses a factor of 32, which, since we are aiming for a small constant, is already quite large. But in the paper, we can avoid this essentially completely. So we can do almost the same, losing only a factor of 1 plus epsilon. And this requires some technicalities that I will just very briefly go over, and then I will go back to this very clean picture. So in the paper, we will instead reduce to constraints that are in some sense a mix of these group constraints and the prefix constraints, and we get them by defining the groups as before, these exponentially growing groups, and then subdividing each group again into a constant number of subgroups and requiring a prefix constraints on these subgroups. So we need to, of each group, we need to select a prefix of the subgroups. This sounds very technical, and it is, but it turns out that essentially all the techniques that we can do for this previous clean problem, they still work very well in this more technical problem. And in this more technical problem, we only lose a factor of 1 plus epsilon here. Of course, the constants here depend on epsilon. But let's, for the sake of this talk, let's just work with this easier problem. So now I will repeat what the problem is we actually want to solve. So we have a structure as in this picture. We have these hierarchically aligned groups. I will sometimes call them rectangles. So we are given these rectangles. Every rectangle is, it can be half of the rectangle to the top. It can also be smaller, but it never intersects with, it never has a non-trivial intersection with its with the rectangle to the top. Now, every rectangle has some cost that we have to pay if we select it. So the cost is basically this sum of the costs of the squares when we select them. And we want to select a minimum cost set of rectangles here, like this blue set, and the constraints that we have to satisfy are given by these vertical red rays. Each of these rays has a certain demand, which needs to be satisfied by the rectangles that intersect with it. So, for example, fix this particular ray, then for this ray only these two rectangles matter because they intersect with it, and if we sum over the weights of these rectangles, they have to be at least as large as the demand of the array. So this is like the definition of the problem, a bit informally, but are there any questions about this? Good. If not, then the second part of my talk will be about how we can solve this problem, or more precisely how we can approximate it. And once we solve it, we immediately get a solution for the scheduling problem. Even though it looks very different, these problems are in fact equivalent up to small factors. And let me also mention a bit the previous work by Bhattacharya and Kumar. So they simplified the same ILP in a similar way, but they arrived at a different problem, a problem on trees. Well, here you also have this kind of tree structure, but they didn't have this precise visualization. And one of the problems, or one of the things that made the lives harder, was that in their reduction, it was not easy to see that the constraints form these nice vertical rays. So we will use a lot that the constraints have this very specific structure. And in the previous work, the constraints had a much more general structure, which required them to use like more involved methods to solve them. For example, this LP rounding method. So the basic roadmap for solving this problem is very simple. We first start by showing that there exists a simple but very structured solution, which is not optimal, but close to optimal, in this case up to a factor of 2+ϵ. And even though it's not optimal, but on the other hand, it is very simple and structured, and this will come in handy for finding this particular solution. Because it's so structured, we are able to, well, not guess the complete solution, but when we restrict to small sub-instances, we are able to actually guess the complete solution on the sub-instance. And then using a dynamic program, we are able to recover the overall solution by merging together the parts that we've guessed. And the first part in this roadmap is the hardest. So I will start instead in the opposite direction with the dynamic program, so that we will see what we actually need from the simple structured solution in order to solve this. So let's look at one particular unit of time, the green vertical line here, and all the rectangles that intersect with it. This could look like in this picture. And we will just assume we have a magical oracle which gives us a few candidates for the solution restricted to all these rectangles. So let me, as you can see, the rectangles, because we have this nice hierarchical structure, the rectangles that intersect with this particular time, they are divided into different blocks of essentially equal looking rectangles. So we have one top block which of the widest rectangles, and then one middle block and one lower block in this case. And let's assume we have this oracle which gives us guesses for how the optimal solution or a close to optimal solution looks like here. So, like I said earlier, a solution is a subset of the rectangles. So each of these guesses corresponds to a subset of these rectangles. For example, the apple might correspond to a certain subset of the top block. This apple corresponds to a subset of this middle block, maybe the lower two rectangles, and the lime corresponds to some subset of the rectangles in this lowest block. We don't have all subsets here. This would be exponentially many, but we have some polynomially many guesses of the solution, and we know among them there's one which corresponds to the solution that we are looking for. How can we now use this to recover the overall solution? We are going essentially bottom up. So let's look at the adjacent time step to the left. So this red time step. Again, our oracle will give us some guesses for how the solution restricted to the rectangles intersecting with the red part look like. For example, it might choose the subset corresponding to apple on the top block, lime on the middle block, and banana on the lowest block. Now, if we want to find out which one is the correct guess, then there's one necessary condition, which is that both of these guesses need to agree on the top and the middle block, because since we assume they correspond to one consistent solution, and these rectangles are the same, the topmost and the middle guess of the correct guess should be equal. On the other hand, the lowest rectangles, they might differ because actually they are independent rectangles. So this already tells us, for example, that apple, lime, banana cannot be the correct guess because there's no guess on the right hand side, which also starts with apple, lime. And the same for apple, orange, banana. So what we can do is combine this guess, apple, apple, cherry, with the guess apple, apple, lemon, and the same for the other guesses. So combining these guesses consistent pairwise and consistently gives us a new set of guesses now for these two adjacent time units. And it could be that there are several solutions or candidate solutions that start with the same subsets. So for example, if there was another guess that also starts with apple, apple, then we would just keep around the one that has the lowest cost. And this essentially implies that in the end, we will again only have polynomially many guesses if the initial guesses were polynomially many. And now, of course, we continue this by looking at again the two adjacent time steps here, and our dynamic program will give us again some set of guesses here, and to combine these together, we again have to look at if they agree on the topmost block. And now in the second iteration, they don't even have to agree on the middle block because these are disjoint rectangles. So the only solution that satisfies is the one starting with raspberry. So we combine these solutions in this way and get an overall solution. And since we are always taking the one with the lowest cost, we can show that this cannot be more costly than the solution that we are searching for. given that there exists these guesses which correspond to one consistent overall solution. Now, having this dynamic program, it's really the question, how can you simplify the instance so that you are able to guess these solutions? And as you saw in this dynamic program, what we essentially need to have is, for the rectangles that intersect with one particular unit of time, we need to guess exactly the subsets corresponding to this solution. And as a starting point, let's just look at one of the blocks. If we want to be able to guess it for everything, we should at least be able to have some kind of guessing procedure for one of these blocks. And this block could look something like this. And we will first group the rectangles by the density, which is the cost divided by weight. So this essentially tells us how expensive the rectangle is. A rectangle is better if it has a lower cost. On the other hand, it's also better if it has a higher weight. So this ratio gives us kind of the utility of each rectangle. And if we round the costs a little bit, we can make it so that there are only a log n many different density groups. In this example, let's just say there are two. There are these blue rectangles that are expensive, and there are these green rectangles which are cheap. And we will now focus on the blue rectangles, and later we will do the same for the others. So let's also illustrate the costs of the rectangles. So even though the blue rectangles have the same cost to weight ratio, they have very different costs as long as the ratio stays the same. So here, for example, the topmost rectangle costs only 1, and the second costs 3. We will start with opt's solution. So let's say opt picks the topmost 2 rectangles here. And now we will construct another feasible solution, which is much simpler and only a factor 2 away from it. And for this solution, we will only use knowledge of opt's budget. So opt paid in total 4. So the first thing we could do is we throw away all rectangles that cost more than 4, because they can obviously not be used in opt. Next, we will greedily select rectangles that are still there, but from bottom to top. So we start by selecting the lowest most rectangle. It costs 2. Then we continue, we select the next rectangle, so we are at a budget of 5. And once we exceed the budget of opt, so in this case this just happened, we will stop our procedure. So we will select from from bottom to top until we have paid at least as much as opt. And why is this only a factor of 2 away from opt's budget? This is because we threw away all rectangles that cost more than opt's budget, and we greedily picked the rectangles. At some point we were still below opt's budget, and then we took 1 extra rectangle. We were above opt's budget, but since this additional rectangle costs only opt's budget once, we are at most a factor of 2 above. And secondly, it's important to notice that this solution, or this transformation to the solution, still remains feasible. And this is essentially because of the constraints, because these vertical ray constraints. You can think of it as it's always better to pick something low, because if some of the rectangles in opt contributed to satisfying some ray constraint, then we know that also the rectangles that are lower, they must also hit the same ray, because the ray, if the ray hit this square, then it must also have hit this square. And since we paid at least as much as opt paid, and we have the same cost and weight ratio, we know that we also cover at least as much with our rectangles. So this essentially leads to that we remain feasible here. And finally, the last part is why can we easily guess this solution? Well, the only thing that we need to know to recover this solution is the budget of opt in this block. And if we guess the budget, we can easily simulate this algorithm and recover the same solution. So we need to guess for each of the density groups the value of opt budget. So naively, this would be values between 1 and n, and log many of them, which would be n to the log n. So here we use that all the values are polynomially bounded. But if you do it a little bit more clever and slightly allow to overguess the budget of opt within a factor of 1 plus epsilon, you can get this down to polynomially many guesses. So with polynomially many guesses, we can guess all these budgets, and then we can recover this structured solution. But there's one more problem, namely, we need to do this somehow for each of these blocks, because of how the dynamic programming works. We would have to do all these polynomially guesses for each of these blocks, and because of the exponential growth of the length of the rectangles, there can only be log n many of these group blocks, but still this would be quasi-polynomially many guesses. And with all of this, you kind of already get a sense of why it's so much easier to do something in quasi-polynomial time than in polynomial time. So we need to somehow change our guessing scheme a little bit in order to have only polynomially many guesses for all of these blocks. So here I will really only give a very high level picture of what is happening. What we will do here is we think of each block as donating a little fraction of its budget to the block below it, or more formally to both blocks that can be below it. And the block below can then use this budget to buy extra rectangles. So this budget will be used to essentially buy all the really good rectangles which have a very good density. So let's take the middle block. It gets some additional budget from the block above it, and it will just start buying rectangles of the best density and so on until it used up all this extra budget. And so, for example, the middle block might be able to buy all rectangles with a density in this region. And maybe the lowest block, it might even be able to buy all rectangles within this region of densities. This spending this extra budget and buying these very good rectangles, it allows us, on the other hand, to drop certain rectangles of the block above. So if we make sure that the block below it, well, it bought extra rectangles with a very good density, this means also it covers a lot more of each of the rays. So then we can again drop some of the rectangles that have a very bad density in the block above. And what you get then is this structure where, recall that previously we had to guess the budget for each of these densities and each of the blocks. But now the budget of in the red region and in the green region, we don't actually need to know it, because the algorithm or the solution is trivial on this, on these budgets. It either buys all the rectangles or it buys none of them. So the only densities that remain non-trivial, for which we would actually need to know the budget, are the densities that are not red and not green. And by doing some work, you can show that the number of non-trivial densities that remain is actually just the order of log n. And as I showed you earlier, for order log n budgets, we can actually guess all of these. So given this better structure, we can actually guess all the densities, and we can guess all the budgets that we need to know, and then we can recover the solution for all rectangles that intersect with a particular unit of time. So let me summarize now what we did. We introduced this geometric visualization of the covering constraints in this integer program, which kind of extends the approach by Bhattacharya and Kumar, but it also simplifies the approach a lot, because we now had a much better structure on the covering constraints. Then using the simplification, we could actually generalize the dynamic program to handle even more complicated geometric problems where the reduction loses only a factor of 1 plus epsilon. So also in the previous work by Bhattacharya and Kumar, because of these complications, they lost a lot of constant factors here and there, and we could reduce the constant factors that we lose to only one place, namely in this argument of the greedy algorithm that I showed, where we picked the rectangles from bottom to top and we overshoot the budget by a factor of 2. This is essentially the only place where we still lose some constant factor. And of course, one interesting remaining direction is if you can actually also get rid of this factor and really get a p-test for this problem. So as a final slide, I want to look at, or I want to give some more recent I want to explain, or I want to tell about a little bit of more recent work where, together with Bansal and Svensson, I handled cases of this problem with multiple machines, and this will be the final slide with just stating the result of what will appear soon. So if you look at the same problem for multiple machines, then already in the non-unweighted case, so where all weights are equal of the jobs, this is highly non-trivial, and essentially if you introduce also weights, then it becomes hopeless to get any meaningful approximation guarantee. So we looked at the unweighted case with multiple machines, and in the most general unrelated setting, this means a job can have actually different processing times depending on which machine it's scheduled on. And we got a result of order log p times square root log n for the minimizing the sum of flow times. And here log p is, or p is the maximum ratio of biggest processing time divided by smallest processing time. And it's also known that you cannot avoid a factor or a factor of log p. So this result is already very close to what we can hope for, up to this factor of square root log n. And we also got a new result for maximum flow time, where you don't want to minimize the sum of flow times, but you want to ensure that every job is processed within a specific time. And for this variant, we get a guarantee of order square root log n. And in both, it's kind of the open question left to get rid of this square root log n. This is based on very different techniques and ideas using results from discrepancy theory. So I just wanted to briefly mention this, and now I want to finish my talk. And yes, are there any questions?